Ready? Okay. Oh, you want me to start? Okay. You guys ready to start? Yes. This is the sixth one. Okay, hi everyone. Thanks for coming. Anna Rosen, you've probably seen a lot of emails from me and others. So this is the sixth annual Heidelberg meeting, and this year we're going to focus on linking observations and simulations. And we're happy that you guys are all here. So I'll pass it on to Alyssa and Thomas.
Okay. So for those of you who don't know, my friend Thomas here took me out for a 4-hour coffee in Heidelberg like 7 years ago and said, we should have these meetings. And here we are. So if you enjoy yourself, you should thank Thomas. And so my job this morning, other than to say hi, thank you very much. And one very important thing. Everybody who is on the organizing committee here, could you please stand up so everybody can see who you are? I know who you are. That is Anna Rosen, Shmuel Bialy, Mike Foley, and Catherine Zucker, who's going to keep you on time, too. So watch out for Catherine. Okay. So they can also help you, and as can Jody Blackwell, who did a huge amount of organizing for this. She's in the back. She's going to get herself a name tag later. But you should remember, Jody knows everything if you need something. And so you've all seen the website for the conference, and the one thing that it falls to me to explain before we move on is the unconferences. And just to show you where that fits in, this is the schedule for the meeting. And for those of you who've been, raise your hand if you've never been to Harvard Heidelberg meeting before. About 10 people. Okay, so talk to the people who are with you. That's going to be the best way to understand what's going on. Okay, but basically, like at least half the time or so is a little bit unscheduled as of now, because we have these things called unconferences. Because a lot of us work on topics of common interest or tangentially interest, and so we like to just talk with each other in ways that are not planned in advance. And so that's what these unconferences are. And in order to facilitate that, there are these introductory talks where everybody will talk for 2 minutes to just kind of say what they're working on these days. And unfortunately, we can't do them all today, or we would spend all day doing that. So there's a schedule, and I'm sure you've all found your name on there. And if you haven't uploaded a Google slide or made a Google slide of what you want to show, you should do that. You have many emails explaining how to do that. But that's how that works. And then we have these framing talks, which you can read about, the highlighted research talks. And then, like I said, it's my job to tell you about the unconference talks. If you want to, and I'm guessing probably no one has, there you go, there's a Google Doc that just says glue tutorial for what these unconferences can be. But in fact, the way that we will schedule them is there are big white pieces of paper with markers that look kind of like this on the other side of the street where we're going. So part of the meeting is going to be here in this room, and then the smaller room is where we're going to have these unconferences and also coffee and stuff like that, or in another building called Pforzheimer House on the other side of Garden Street. And again, just walk with people from here, and we'll show you where that is. Okay, and so this horrible looking document shows you what is going to happen at these unconferences. And so all I need to really tell you is that each one has a chair. So when you propose something, so you're going to write down on these blank sheets here an idea. It says, like, I want to talk about W49 because it's my favorite region, or I want to talk about, I don't know, unicorns in space. Okay, like whatever you want to talk about, you write that down, and then other people during a break are going to put little tick marks if they're also interested in that, and then the ones that the most people are interested in will get a room during the next unconference session. And if yours doesn't get chosen for that session, we can schedule it for a later session. So in other words, I think there's 3 rooms for unconference. We can have 4 at a time, but there's 5 sessions or something of unconferences. So there's a lot of time to do these. And again, the experts who have done all this all before, just ask one of them if you're not sure what to do. But the important thing is that there's a chair, who is the person who proposed the topic, and your job as the chair is not to say too much, but it's also to make sure that no one else says too much. So it's supposed to be a conversation. And if you want to show slides or images or movies or whatever, there's instructions here about a Google Drive folder where you can go, whoa, TinyURL just broke completely. It wasn't just yours. We just tried this 20 minutes ago.
It's not my fault.
All right, we'll put the real link. We'll change this so that it's not a TinyURL. But anyway, there's a folder on Google Drive. Can you fix it?
Yes.
I'm just going to some long, horrible link. Yeah, okay. Anyway, where you can put any slide or image that you want to show in the unconference, and then that way people don't have to unplug and plug in their computer. There are computers in each room, or computer hookups in each room. Okay, and then somebody, the chair should designate somebody as a recorder. Somebody should volunteer to take some notes. And in that same folder where people upload images and whatever, just take some notes in a Google Doc, even if it's just the name of the unconference, if you don't want any notes. Okay, okay, and there is an exception to not talking too much, which is that if somebody has a software package that they want to talk about or something else that would get a tutorial, you can propose to have explicitly a tutorial. And then people should know what they're getting into. They're going to learn about some software. And if there's like related software packages, I think it would be fine to find a pal who has one that's related to yours and propose one that's a twofer. Would be great. So, okay, any questions about the unconferences? No? That sounded sort of clear? Okay, and so then do I turn it over to Thomas? And then what web page do I want to be this computer on?
The Google Slides.
The Google Slides, but now all the...
Which is that broken?
If you
Go to the homepage, there's a long link on the homepage.
Okay.
Yeah. So go to home.
Oh, we're just home.
Yeah.
Okay.
And then go to Google Slides presentation, and that's where it brings you right to it. Yep.
Okay, good. So there we go. Okay, fine. Here we go. That should be fine.
So I think, Phil, you're up. Phil, I think you're the first one.
Yep.
So I'm going to have a big timer on my computer. Yeah. And so you have a few minutes.
Okay.
Oh, God.
Oh, sorry. I'm sorry.
Thomas is the chair.
Sorry,
If you help me, there's a time.
Thomas is the chair.
Yeah, you're right. Thomas, you tell me what to do.
Well, first of all, it's a great pleasure to be back here. I couldn't imagine that this is already the 6th edition. It seems to be. Time is flying. We really had very good meetings in the past, and I hope for a lot of interactions during this week. I guess that is also the reason that we have these unconference sessions. They were always very good, and I think it will be good this week as well. And we just start right away with an introductory talk, and Phil, you are first.
Yes, works. Okay. Good morning, everybody. And my job is to tell you about some work that I've been doing with Ian Stevens, Shantanu Basu, Sayantan Audi, and several other folks. And the idea is to try and learn more about magnetic fields in star-forming regions. We know magnetic fields are important for many aspects of star formation. It's listed here. And so the goal is to be able to get better estimates of the strength and the structure of magnetic fields in star-forming regions. Present techniques for extracting field strength all have their limitations. So we've undertaken 2 new ways to infer magnetic field properties in star-forming regions, and they are based on 2 very old ideas. One is the idea of flux freezing, which was pioneered by Leon Mestel many years ago, and the idea is probably familiar to many of you. You have a initially relatively uniform medium threaded by a uniform field. It is going to condense and compress, and the field is dragged in because the field is a little bit weaker than the forces doing the compression. It gives you an hourglass shape to the field lines and also to the polarization. And the field strength scales roughly as the 2/3 power of the mean density, which has been verified in a number of Zeeman studies summarized by a well-known paper by Dick Crutcher. What makes our contribution new? It is that we have gone from the spherical case, which was analyzed by Nassel, to the spheroidal case, and that means that we can apply this to regions which look relatively elongated or flattened or non-spherical. So nearly all observed regions depart from beautiful symmetry, of spherical symmetry. And when you analyze the problem in the spheroidal case, such as a p equals 2 kilometer spheroid, then you have to take into account the elongation and the inclination and the aspect ratio, and so we have now done all that. And we are able to do this estimation of field strength based on spheroidal objects with flux freezing. The second old concept is that Alfvén waves on magnetic field lines are linked to the velocity dispersion that we observe in the spectral lines, and also the mean density and the dispersion of polarization, the Chandrasekhar-Fermi technique for estimating field strength from polarization observations. And what's new in what I'm going to show you is that if you assume a certain mean level of field fluctuation, then that enables you to get the mean field strength from the non-thermal part of the line width and the mean density of the region that you're studying. And this has become especially attractive now that we have so many beautiful maps of the ammonia lines, which allow us to separate the thermal and the non-thermal parts of the line width very easily. Okay, so just to illustrate how this might work, here's an application to a well-known star-forming core. It's formed a protostellar binary, BHR71. Here's an ammonia map made at Parkes on the 0.05 parsec scale. And estimating the field strength and structure is as easy as 1, 2, 3. Here are the 1, 2, 3 steps, based first on magnetic turbulence and then secondly on flux freezing. And that allows you to get the run of field strength with position and also the field direction positioned in the map. So here is the run of field strength running from about a minimum of about 35 microgauss in the background level up to a peak of about half a milligauss. And this is scanning along the two perpendicular directions. Since the region is not spherical, it's elongated, you have to take that into account. How am I doing?
-2.
Minus?
Yeah, minus.
The final point is that you can use this to evaluate the mass-to-flux ratio. We get a value of 2, which means that star-forming gravitational collapse would now be allowed, and that is reassuring since we have already formed 2 stars in this region. So this application can be applied to now large samples of clouds and cores, and you can get a good idea of what the mass-to-flux ratio will be.
The idea is to have discussions later, so they have the short forms all the time.
You say return, Phil, so we say who's next.
Who's next?
Okay, return, sorry.
The next speaker is Liu.
Hi, good morning everyone. I'm Junhao. I'm presenting AMA 1.3 millimeter polarization observation toward 3 massive clumps in the infrared dark cloud G28 to investigate the role of magnetic fields in the early stages of massive star formation by analyzing the angular expression functions of 2 massive dense cores in clumps M1 and M4. I estimated the magnetic field strength and studied the dynamic state of the 2 cores. Calculations show that even with account for the magnetic support, the variable parameters are still less than 1, which signifies a more dynamic massive star formation in non-equilibrium. I also compared the outflow axis with the magnetic field orientation in clumps M4 and mm9 in the condensation and found an approximate bimodal distribution suggesting that magnetic fields might play an important role from condensation to risk scales in the early stage of massive star formation. Besides, I applied the angular dispersion functions method developed by Martin Houdet on simulated ARMA observations of 3D MSD simulations of massive star formation and found that the estimates from this method are generally accurate within a factor of 2 factors at scales close to the thin scale and the further scale. This method might underestimate the manifold scales.
So next contribution is by Monica.
So good morning everyone. So my name is Roman Loyal and I'm a postdoc here at the CHP in the group of Heidelberg. So I'm working in astrochemistry for 8 years now, and with Karen during the past 2 years we have focused on the chemistry of planetoids in particular. And so today I wanted to highlight
Make sure it's on. Sorry. Sorry about that. We thought everybody would be able to hear, but turns out it's hard to hear in the back.
It's working. So today I wanted to highlight in particular the result of our latest paper accepted in ABJ, where we show the importance of the C/O elemental ratio in the chemistry of PDRs and planet-forming disks. So PDRs are the acronym for photodominated regions, which are found wherever there is an interface between diffuse and dense gas in the interstellar medium. And a famous one is the Orsed Nebula, which have been observed a lot, and in which the chemistry was also deeply explored. More than 30 species have been detected, and in particular the 3 cyanides I'm showing at the very bottom. Is this working? So these 3. And so we focused in our study on those 3 molecules because they are also observed in disks. And before our study, it was not very well understood. In particular, their abundance couldn't be reproduced. So what I've been doing, I further developed the PDR Meudon code, in which I extended the chemistry to these 3 molecules and explored different parameters on the chemistry. So here I'm showing how the abundances of these 3 molecules are varying as function of the visual extension, so within the PDR. For different C/O ratio, varying from 0.4 to 1.5, and where the dash boxes represent the observation within the arrow bars. And what we show is that when you vary the C/O ratio by less than a factor of 4, there is more than several order of magnitude change in the abundances of these 3 cyanides. And in particular, we need a C/O ratio of 0.9, so which is higher than the solar value, which is 0.5, to reproduce the abundances of the 3 molecules. So we wanted to test our findings in disks, because the outer layer of disk can be compared as photodominated regions. So for that, I've been using disks that we already published earlier this year in another ABJ paper. And so I took this model and I focused in particular on the chemistry of CH3CN and HC3N, so which are both observed in several disks. And we show that indeed for a C/O ratio, an elevated C/O ratio, so of 1, we can better reproduce the observations that have been observed. So this is an interesting result because it also explains why you would have more species like CH3CN rather than CH3OH in disks because of the C/O ratio. And it's also in agreement with other results that are currently found in disks. So if you want more detail, you can come talk to me, or you can look at the paper also, which is on arXiv.
So next Next talk is by Ian Stevens. I guess magnetic fields should be somehow.
It'll be in there somewhere. All right. So the first thing I'm going to just kind of mention, because it's the main thing. So, I'm Ian Stevens. I'm a postdoctoral fellow on the Smithsonian side. And so the main thing I've been working on here is the MASSA survey, which is along with CM Zoom, it's the largest survey ever done by the SMA. And it's a survey that's complete of all class 0 and class 1 protostars, every single one in the Perseus molecular cloud. And we look at size scales from 1 to 20, about 1 to 20 arc seconds is what we're sensitive to with SMA. And this is the only complete survey at those size scales of molecular lines and continuum. And we can see you got a lot of beautiful special lines. What you see on the left is CO2 to 1 outflow. You got CO2 to 1, and you see these really textbook outflows that we're mapping, many that have not been mapped before. And we already have 10 published papers with this survey, and the data is publicly available. The full catalog's just accepted. And then I'm also going to be presenting a poster, and it's going to be a lot of polarization. So here's some beautiful polarization images I've been taking with Sophia. This is Snake, G18.6. This is most of NGC 1333. Here's some stuff in Orion B, NGC 2068 and 2071. I've also been trying to do line polarization of disk, and apparently it's very, very tough. I don't see any vectors here, but these are 2 disks I've been looking at, and it seems like the GK effect, line polarization, is less than 1% polarized for these disks, which was kind of surprising. And then I also will talk, if you want to talk with Phil and me about the spherical flux freezing model he's doing, we're both working on that. Here's some things that we're doing when we're fitting polarization morphologies. Thanks.
Thank you. Now we will move to the framing part. So the first part is by Simon Cover from the Institute for Radioactive Physics and part 5 simulators.
What should I do with this laptop?
Oh, sorry, she gave it to me. Thank you.
Okay. Is the microphone on? Okay. Right. I'd like to start by thanking the organisers for inviting me to give a talk about chemistry and why it's interesting and why it's difficult. So, the ISM is actually chemically a really interesting place. Even though by terrestrial standards it's a really harsh environment, it's close to a vacuum terrestrially. There's all these high-energy cosmic rays, lots of UV photons. Despite this, it's a really chemically rich place. So this is just an actual subset, because I couldn't fit all of the species on the slide, of all of the chemical species that have actually been detected in the ISM. Now, a lot of these are in circumstellar gas, but there's still quite a few of these that have also been detected in interstellar clouds. So that's really a lot of complexity. And we'd like to model that. And really, historically, there have been 2 main reasons put forward for why we might be interested in modeling the chemical composition of interstellar gas clouds. One is that we know molecules are really good low-temperature coolants, in particular things like CO. And so if we want to get the thermal state of the gas correct, we might be interested in its molecular composition. And the other thing is that there's a wealth of data on the physical conditions in the interstellar gas that's encoded in the molecular lines and in the chemical composition. And if we want to actually interpret this, we actually need to be able to model the chemical composition. Now, I mean, this has been done for a long, long time by astrochemists in simplified models, starting with kind of 1-zone models and moving towards kind of 1D static models or even 1D evolving models. But really, we'd like to do this in full 3D simulations where you have all of the messy hydrodynamics. And this turns out to be quite hard. So why is this hard? It's basically because the ISM is so chemically rich. We've got hundreds of species, thousands of reactions. So this is an example from the from the latest release of the UMIS database for astrochemistry. That's got almost 500 species in it, linked by of order 6,000 gas phase reactions. And if we're interested in things like deuteration or grain surface chemistry, then these numbers just go up even further. And so if we really want to comprehensively model all of the chemistry in the ISM, we have to handle all of this. And this is a problem. Now, each of these individual species has a partial density. If we add up all these partial densities, we get the total gas density. And the partial density of each of these species has a governing equation, which you can write like this. So these two terms on the left-hand side, that's just the usual continuity equation, basically describing how our partial density of this particular species is getting advected around. Then we have this term, which is representing diffusion. This is basically microscopic diffusion. If we have a chemical inhomogeneity, even if the gas is not moving around, then microscopically it will mix. And then we have these terms on the right-hand side, one representing the creation of new instances of this species. So say this is a molecule we're interested in, this is the formation of the molecule, and this term, which is the destruction of the molecule. Now, in the ISM, we have one simplification we can usually get away with making, which is to ignore the diffusion term. That's because generally the advection term is much more important, and it's like the turbulent diffusion is much more important than molecular diffusion. So we can throw that away. But that still leaves us with a set of advection reaction equations, one for each species. And now what we generally do in order to solve these, we do something called operator splitting. So rather than solving this complicated partial differential equation, we break it into two things. We break it into a normal partial differential equation with 0 on the right-hand side, which just describes the advection of our species. And then we have a separate ordinary differential equation which describes the chemistry, the reaction term. Okay, so this is just first order ODE. Those are easy to solve. So what's the problem? The problem is that there are lots of different processes basically encapsulated in these terms that have a very wide range of different timescales. So chemistry occurs on a wide range of different timescales simultaneously. You can think of something like H2 formation in the ISM. The H2 photodissociation timescale in unshielded bits of the ISM is very short. The actual formation time is very long. So you've got an order of magnitude different in the characteristic timescales. And that means that these ordinary differential equations are what we call stiff. So now, stiff is just a shorthand way of saying they span a wide range of timescales. But this presents us with a problem. And to illustrate the problem, it's convenient to think of a very much reduced dimensionality version of the problem where we basically have two different timescales, a short one and a long one. So suppose we have our system that starts in some chemical state. It's not going to start in any kind of equilibrium, but any fast reactions, the short timescale reactions, are very quickly going to come to equilibrium. So the actual chemical evolution is mostly going to occur on some reduced dimensionality surface in our chemical state space. So if it's hard to draw a high dimensional surface here, so I've just drawn a line instead. So basically, if we start at some point up here, the rapidly occurring processes quickly take us to this line, and then the slow reactions move us along this line. Okay. So, what is the problem? The problem is, if we try and solve the ODE describing this behavior explicitly, so basically calculate the time derivatives at this point in time, and if we're not on this slow manifold, if we're sitting off of it, then we're going to get a very large gradient, because we'll pick up the influence of these fast reactions. So to accurately follow the evolution, we have to take very small time steps to make sure that we reach this slow manifold and don't massively overshoot it. So that's fine. But every time we go to a new hydrodynamical time step in our simulation, we're going to get displaced away from this slow manifold. This is inevitable. We have truncation errors, we have round-off errors, we have advection effects. They're all going to introduce some error that's going to move us away from this equilibrium state and put us in a point where the fast reactions are not in equilibrium. So every time we try and solve the ODE, we're going to have to take these really tiny time steps, which means we wind up taking enormous amounts of time to solve these ODEs and actually to solve the boring bits, the bits that we don't care about because we know actually the system's going to be in chemical equilibrium as far as these fast reactions are concerned. So this can be just like horrifically expensive computationally. So the usual way to get around this is to solve them implicitly. So calculate our time derivatives at the end of the time step rather than the start of the time step. This is a well-established technique for solving stiff ordinary differential equations. The problem is it's an iterative technique and you have to do a matrix inversion. And that is also costly. That has a cost that scales as the cube of the number of reactions you're dealing with. Not reactions, species. So if you're just dealing with a small handful of species, that's fine. If you're dealing with 500 species, that's also horrific. So the consequence is that the full chemical network is very costly to solve, and while you can do it fine in kind of 1D approximations, to do so in a 3D simulation where you have millions or tens of millions or hundreds of millions of resolution elements is just not practical. So what do we do? Well, one very useful technique we can use to get around this is using what are called reduced networks. And the idea here is pretty simple. If we're just interested in something like ISM cooling, we know that most of these of order 500 species are not important. If we go back to the list at the start, the abundances of many of these things are really small. They're not going to contribute in any meaningful way to the thermal balance of the ISM. So we only are actually interested from a thermal point of view in the abundances of a fairly small number of species, like C+, atomic oxygen, CO, H2, a few others I haven't bothered to list here. So we can make a really big computational saving if we design our network to just follow the chemistry of these species and not all of the other complex chemistry. So this simplified chemical network, the jargon is this is a reduced network. And if we can reduce, say, the number of species we have to track from 500 down to order 15 or 20, remember our cost is going as the species cubed. This is like factors of 1,000 saving in computational time. So this has been explored for a while in the literature. There's a number of different examples designed to follow specifically CO chemistry because that's one of the simpler but more important things. I can go into boring detail about this if anybody's interested, but I'll save that for the coffee break. But the current state of the art, there's two kind of networks I would say are state of the art. So there's one which, if you're interested in speed and don't care much about accuracy, there's a network that Paul Clark and I put together, which basically is a simple description of the hydrogen chemistry plus a single reaction approximation for CO formation and destruction, which is based on the work of Nelson and Langer. Now this is really fast. You wind up with having basically 3 reaction equations you have to follow, and it's hard to do better than that if you want to model H2 and CO. It's not very accurate, but it's a good choice if you're doing a large-scale simulation and you don't have much resolution in your individual molecular clouds. It will give you the right behavior in the limits of low densities and low column densities and high volume and column densities. It doesn't do very well in between, but if you just want to know, is this cloud molecular or atomic, it's a good choice. So there's a lot of work already been done using this. If you do have enough resolution to actually resolve cloud structure and you want to do a better job of modeling the transition from atomic to molecular gas, we can do a lot better. There's a few different possibilities in the literature, but I think the current state of the art is this network that Munan Gong published last year, which is based on earlier work by, again, by Nelson and Langer that Munan has improved. So I've just got a couple of illustrations of what you can do with these things. So this is some work done with the Nelson Langer 97, really simple network. So this is a model of the central molecular zone of our galaxy. So this is the bar, this is gas falling along the bar, and you see this ring develops in the middle. But specifically let's try that again. Specifically, what we're looking at here is a synthetic image of the C+ fine structure line surface brightness. So we're following where the molecular gas is, where the ionized carbon is, and looking at what you would see if you were looking from outside our galaxy, looking down on the central bar and the ring. Okay, and this is a plot from Munan's paper, a very complicated plot of a range of different species. Basically, her results are the solid lines, and the dashed lines are what you get from Mark Wolfire's PDR code, which has got a much more complex chemical model in it. And what you're supposed to take away from these is that there's a good agreement between the solid and the dashed lines in most cases. There are a few things, like atomic carbon, where there's a factor of few disagreement, but on the whole, her reduced network does pretty well for a much smaller cost than in the full PDR network. So there's various things you can do with this. Now, one of the first things that we did was to look at the actual role that molecular cooling plays in star formation. Because, as I said, like historically, people have always said, "Oh, molecules are really important because you need molecular cooling to form stars." Yeah, it turns out that's not true. So this is from a paper we published back in 2012. Where we basically ran a series of simulations of the same turbulent molecular cloud, just successively turning off bits of the chemistry. So you go from the full model with different initial conditions to one that's just tracking H2 formation and destruction to one that's just assuming all of the gas is atomic. And in the end, they all form stars. There's not a huge difference in the ability of these clouds to form stars, depending on whether they're molecular or atomic. We've also seen a similar result in simulations of dwarf galaxies. So this is from some work by Chao-Yu Hu from a few years ago, looking at a dwarf galaxy with a metallicity of 1/10 solar. And what he did here was vary various parameters like the strength of the interstellar radiation field or the dust-to-gas ratio. So this is these three colored lines at the top. And that makes a huge difference to how much molecular gas you form in the galaxy. This is the H2 mass fraction, which is varying by more than an order of magnitude as you play around with these parameters. But when you look at the actual star formation rate, it doesn't really make any difference. The only thing that makes any difference to the star formation rate is turning off the feedback, which then gives you this green line. So yeah, it turns out while molecules are important in actual molecular clouds, if they weren't there, you'd form stars anyway, with pretty similar properties. From one point of view, this is good. This means that we can probably trust a lot of the simulations of large-scale star formation in galaxies that have been done without molecular chemistry. They're not going to be making huge errors. From another point of view, then it does lead one to think, why did we spend so much time trying to get this to work in the first place? Well, fortunately, there is another reason why the chemistry is interesting, which is using the chemistry as a tracer of the physical conditions. And fortunately, a lot of the things that we're interested in, because they play a role in the thermodynamics of the gas, are also interesting chemical tracers. So CO, again, is the obvious one. We started trying to model CO because we were interested in it as a coolant, but we then get its distribution as a tracer for free. So some of these things we can treat nicely with these reduced networks. So we've done a lot of work on C++, C, CO, because we have these in the reduced networks. But then there's a lot of other interesting tracer species, which are not included in the current reduced networks, but we'd still like to know about. And this is, good examples of this are the classic high-density tracers. So HCN, CN, N2H+, CH3OH, etc., etc. And to model these, to model the full range of interesting tracers, well, we could try and come up with more complicated reduced networks, but this is a fairly time-consuming process, and it's less of a saving the more chemistry you have to follow. So generally, the techniques that people use here are more reliant on post-processing. So you run some simulation and then you try and do the chemistry afterwards. Now you can't do this if the chemistry is important for the thermodynamics, because obviously if you do it afterwards, you can't account for its influence on the actual thermal evolution of the gas. But for these things that are not important thermodynamically, but are just interesting as tracers, there's no problem in just trying to paint them on later. So there's a couple of main approaches that people have used here. So one approach, probably the simplest approach, is to just assume a chemical equilibrium. So take a snapshot from your simulation with some complicated density structure and just solve for the equilibrium chemical abundances. Now there's two different ways of doing this. You can take the temperature directly from the hydro simulations and keep that fixed and then just solve for the chemistry, or you can solve self-consistently for the temperature and chemistry in this post-processing step. And that latter approach is what you do if your actual original hydro simulation was done with an isothermal approximation, for instance. Now the main complication here is that generally we need to worry about the attenuation of the radiation field. So generally you're not just solving the chemistry, which would be fairly straightforward, but you're also solving for the radiation field at the same time. And if you need to account for things like H2 self-shielding, this actually becomes an iterative process. You have to solve for the radiation field and then solve for the chemistry, and then the chemical state is going to modify the radiation field, so you go backwards and forwards until you wind up with some equilibrium solution. There's a couple of examples of this. So one which I'm going to show a result from in a minute is Thomas Bisbas's 3D PDR code, and there's another one, TurboChem, that Shmuel is going to talk about later this week, so I'm not going to say anything about that. But this is what you get from TurboChem. So this is from a paper by Brent Gatchis from a few years ago. Basically what he's done here is taken a simulation done by Seller-Offner, which used just isothermal turbulence, and post-processed it with 3D PDR to produce maps of the different chemical species shown here. So you see what you see in a tracer like CO is actually very different from what you'd see in a higher density tracer like N2H+. So this is fine, but you have to assume chemical equilibrium. So what if that's not true? What if your species are not in equilibrium? And we know that some things are probably not going to be. Some things will go quickly to equilibrium. Some things like H2 go very slowly to equilibrium. So the other approach that tries to capture these time-dependent effects basically uses what are called Lagrangian tracers. So these are basically just tracers that go along with the flow and allow us to record the state of a particular fluid element as a function of time. So its density, its temperature, and also the radiation field it's seeing, just as a function of time as that fluid element evolves. And if we store all of that information, then we can later run that through our chemical evolution code to figure out what the chemical history of that fluid element was. Now this has the big advantage that there's no need to assume equilibrium, but it has a disadvantage in that generally when we put our tracers in at the start of the simulation, we don't know where they're going to end up. So there's always the danger you're not going to actually sample all the regions you're interested in, or you're not going to sample it well enough. And that's something that we're still kind of struggling with figuring out the best ways to do this. So this is an example of basically how you would do this. So this is from a paper by Laszlo Zuchatel, currently still in prep. So you start with your hydro simulation, you select some regions, you post-process them with a chemical code. In his case, he was using Dima Semenov's alchemic code, and then you stick them on a grid, and then you can run radiative transfer on that grid to make emission maps if you want. So this is an example of what you can get. So this is the underlying hydro simulation, which is an SPH simulation of a 10 to the 4 solar mass cloud. He's zoomed in on one particular region with a few different cores and put in tracers to sample this region. And if you do that and then look at the later chemical state using these tracer-derived chemistry, you can see we can do a fairly good job of following the evolution of different species. And again, we see that like your classic high-density tracers are really just concentrated in the cores. CO is much more extended. There's lots of information we can potentially extract from this. So we're not the only group that's been doing this. There's also a paper from John Illet from a couple of years ago. They've done something very similar. In that case, they were looking at disk chemistry. So this is some protoplanetary disk with several fragments formed in it, which for some reason he's called John, George, Paul, and Ringo. And because this is an SPH simulation, the SPH particles are actually Lagrangian traces themselves. So what John Illet did was basically take every single SPH particle, look at its history, and run it through a chemical model. So there's order a couple of million SPH particles in the simulation, and apparently if you just kind of use every single node on the cluster for a week, you can post-process all of the chemical history of every single particle and make these detailed predictions for the chemical makeup of the disk. Okay, I have no idea how much time I have left, so.
You have 10 minutes.
Oh, I've gone a lot faster than I thought. Okay, so then I've got time to just show off a few examples of what we can do with models of the chemistry of the ISM. So these are a fairly biased selection of work that we've done. And I can talk about them more at length in the coffee break or in the discussion afterwards. So this is the first one. There's been a question for a long time. If molecular clouds form in converging flows of atomic gas, how do we actually trace this process? The molecules, by definition, form in the cloud once it's assembled. We're not going to be able to trace the inflow by looking at CO. We might have some hope of seeing subsignature of that in H1, but H1 is tricky because it tends to have large velocity widths, so it all gets very confusing. So people suggested, well, C+. C+ should be a good tracer of this lower density inflowing material. So does this actually work in detail? And so this is something that Paul Clark and I looked at in a paper we published this year. And so these are position velocity diagrams of basically a colliding cloud experiment. We have two clouds with turbulence, we run them into each other, and then we make synthetic emission maps to see where the emission's coming from. And so we see for the CO, or the two C1 fine structure lines, this emission is all coming from a pretty narrow range of velocities. This is basically the molecular cloud itself, half that's formed in the collision. Whereas if we look at C+, we see this much broader range of velocities, so we are actually successfully tracing the inflow. The problem is, if you look carefully, in particular if you look carefully at the scale, yes, there's lots of emission out here. It's pretty faint. It's brightness temperatures of tens of millikelvin. So this turns out, yeah, it is possible to trace this material in C++, but it's really, really hard to do that. So our original hopes that you'd be able to just kind of point Saphir at some patch of the sky and map all of this doesn't really work. It's too faint to map. What you can do is just point at one patch and you can get detection. So Nicola Schneider's got some nice, not yet published C+ detections, just looking at individual points near kind of high latitude molecular clouds. A second example. So this is now actual data, not synthetic data. So this is position velocity diagrams of the center of the Milky Way, mostly looking at CO. This stuff is NH3, ignore that. And it's been understood for a long time that there are these odd so-called extended velocity features where at some particular galactic longitude you see this very broad vertical feature in the PV diagram. So there's a very wide range of different velocities at one longitude. And what I'm not showing here is these are actually fairly spatially coherent as well. If you look at the longitude, latitude, they tend to just sit in one space. They're not extended on the sky. So for a long time, there's been discussion about what are these things. It's even been suggested that these might be intermediate mass black holes falling into the center of the galaxy, and that the large velocity widths you're seeing here is the gas spiraling around the black hole. we have a different picture. So this is basically a fairly complicated plot from one of these galactic center simulations I showed you earlier. So this is the bar. The colored bits here are gas streaming along the bar and winding up in the center. And if you look at this in a PV diagram, so galactic longitude velocity, we see that we also recover these extended velocity features quite naturally in the simulation. But what we can then do in the simulation is say, okay, well, right, we see this in the PV. Where is this in actual real space? And what we find is that these bits where you have this extremely large extending velocity, these are actually out in the bar where individual streams of gas are running into each other. So they're nothing to do with the actual CMZ itself. They're basically, what happens is some of the gas that falls in along the bar misses the CMZ, overshoots. Instead of running into the center, it misses, it comes around the other side, and it runs into the gas that's falling down the bar from the other side of the galaxy, and you have a big collision. These collisions are spatially coherent, and you naturally get these very extended velocity features. Right, and finally, this is from some work by Gowin Jones, who's a student in Cardiff with Paul Clark. So what we've been doing here is looking at HCN and trying to figure out where does the HCN emission in a dense cloud actually come from. So this is our emission map of HCN in the cloud. No, it's not. This is, yeah. So this is the total emission in Kelvin kilometer per second. You see this complex structure. So what Gowin has then done is basically done a succession of different radiative transfer models where we basically only include gas above some density threshold. And as you change the density threshold, you can ask, well, when does that emission map start looking like this total emission? So if you just include the gas above the number density of 10 to the 4, so this is classically what people have assumed HCN is tracing, you get this. This does not look very much like this. If you go down to 10 to the 3, then you get much better agreement. So in this particular cloud, the conclusion that we come to is that actually the HCN emission is mostly coming from this range of densities between 10 to the 3 and 10 to the 4. So the densities it's tracing are quite a bit lower than people have previously anticipated, and certainly orders of magnitude lower than the HCN critical density, which is order 10 to the 6. And while I don't have a plot of this, this seems to be backed up by some observational work we've been doing together with Jens Kaufmann and a large crowd of other people. So this is the LEGO survey of 3 millimeter lines in gas clouds in the Milky Way. So we have some work we're just writing up right now on W49, and that again is showing us that if you map HCN over the whole of the cloud rather than just in the cores, you actually see emission from all over the cloud, which is consistent with it coming from much lower densities than has been previously supposed. So again, somewhere in this range of 10 to the 3 to 10 to the 4. Okay, so to sum up, modeling the chemical composition of the ISM is important for interpreting molecular line observations. Turns out not to be so important as we thought for actually getting the thermal state of the gas right. It's a challenging computational problem in 3D for reasons I've tried to explain. But this is something that we are actually successfully dealing with now, at least as far as the simple carbon-bearing species are concerned. And we're starting to get to grips with some of these more complicated high-density tracer species. But I have to say that while we've got some nice preliminary results there, this is an area which is still largely unexplored. There's really a lot still to be done looking at these lower abundance, high-density tracers and other interesting tracers. And I think we'll hear some more of that from Shmuel tomorrow or the day after tomorrow, whenever he's talking. Okay, thank you.
Thank you, Simon. I think there are questions.
I actually have two questions. One is about the molecules not being important for cooling, which is really striking, although it's not new. But so first of all,
Yeah,
Still different? And
there may be some effect here, but we can't tell with the simulation because these tracks are fairly well resolved. If we go to higher mass resolution, this doesn't change. If we go to higher mass resolution, this changes a lot. So we're not resolving all of the fragmentation here, so it's dangerous to overinterpret this. We might.
So in other words, would you say this question is solved? That it's quite clear that the molecules are only important as tracers and not as coolants, or is it still an open question?
I think the influence that the molecular cooling might have on the IMF is still not entirely pinned down. But I mean, something to bear in mind is the molecules are only important over like maybe 1.5 orders of magnitude in density. So if most of your fragmentation is happening later on when dust is dominating, then the molecule's not going to be important. But yeah, I mean, there's still an element of doubt there. I think from a simulation point of view, as far as the star formation rate is concerned, the molecular cooling is not important, or if it's important, it's not the main thing that we need to worry about. The balance of feedback and cloud formation is much more important than the chemical state of what that cloud is made of.
I think we should continue.
Well, I was going to add to that. So then in that regard, then how important is it to solve the chemical network during real time, or just doing post-processing, or just doing tracers with post-processing? Like, because including more, like doing the real-time chemical modeling as simulations are running is really hard, whereas you can study more molecules if you do tracer particles and do post-processing. Does it make a difference?
Well, the one advantage that you get from doing it in real time is then you do have it everywhere. Whereas with tracers, then you might wind up that you don't have tracers in the regions you're interested in. So if you're actually interested in the chemical composition everywhere, then yeah. But I mean, if you're interested in something like CO, then that's actually potentially quite a large volume review simulation. You want to know what the chemistry is doing. So there are advantages to actually doing it in real time. But yeah, for a lot of things, I think you might as well just post-process it.
Go to the back first.
I was just wondering, so your chemistry is steady state? Or is it time-dependent?
So all of the work that I've shown from our group is doing time-dependent chemistry.
So then I have another question. For the HTM you were showing at the end, how it would, because you said if the results are very different with the density, but how do you constrain the time here, for instance?
This is just looking at one particular output time from this cloud, I think probably shortly before star formation has started. So, I mean, this is still work in progress. So an obvious next thing to do is then look at different points in the history of the cloud. So, yeah, strictly speaking, we don't know this yet. We know at this particular point in the history of the cloud, this is true.
But did you run the chemistry until it converged at least? So if you have a certain time step of the cloud, and then you run the chemistry until equilibrium was reached?
No, because I mean, if you're doing a non-equilibrium model, then at this particular time you're not going to be in equilibrium, and you can't. And you.
If it's fast or not.
Yeah, I would have to ask Owen actually, precisely what they did here.
In other words, if that would change over time, then of course it doesn't make any sense to show that.
Yeah.
Because in this chemistry, we very often, you take this chemistry, you take temperature and density, and then you run your chemical model until it converged, and then you get a feeling, if that is okay for this certain time step or not.
Yeah, I mean, I think one of the big things that somebody still needs to do is really compare what we get from these time-dependent models with what you get from just assuming equilibrium, and get a better sense of like when is equilibrium just going to be a fine approximation and when is it not? And we don't really have that sense yet. But I mean, I think with the different attempts now being done to do this in 3D, that's going to come soon. I mean, I think you're going to say more about that later, aren't you?
Also, there's a big difference between the H2 and the other molecules. So
Yeah, but everything else depends on the H2. So if the H2 is not in equilibrium, then...
That was good back to what you were saying, Shmuel, a minute ago. And so you said, oh, but then the dust gets important at high density. So I always learned that dust was always important. So what are you saying in terms of, you're saying that the reactions in the low density interstellar medium are dominant in terms of the cooling or the chemistry, or what do you mean?
So yeah, I don't have a plot in this particular talk, but if you look at what's dominating the cooling balance of a molecular cloud, at low density it's dominated by C+ cooling. At
Define low density.
below about 1,000 particles per cc. Between about 1,000 and a few times 10 to the 4, maybe 10 to the 5, probably depends a bit on exactly where you're looking in the cloud, you're dominated by the molecules, specifically CO. And above 10 to the 5, you're dominated by dust. You effectively couple to the dust, and then the gas temperature just tracks the dust temperature. Now, all of those numbers are true for radiation fields close to the usual drain field and for solar metallicity. If you reduce the metallicity, then you're going to change where those transitions occur. But for kind of typical nearby molecular clouds, yeah, your CO is only dominating the cooling between number density 10 to the 3 and 10 to the 5, which is potentially important because that's the density at which you form the prestellar cores.
Right, but you made the statement at the beginning that that all your hard work about trying to do chemistry self-consistently, it doesn't really matter because you have these other models that are sort of close enough, right? And then you said that that's okay for the extragalactic case, probably, because they don't usually include molecular cores. But it sounds to me like it actually matters what the balance of gas at different densities is in the models of external galaxies for that statement to be true.
Well, no, I mean, the statement I made was basically, if you didn't have the molecules there, not much would change. The big difference, if you don't have CO, if you just assume all of your carbon is there as C+, is then instead of cooling down to of order 10 Kelvin, you cool down to 20 Kelvin. And that's basically it. You can get almost as cold. It's not quite as cold, so it will change the structure a bit. But, I mean, you're still dominated by non-thermal motions. And really, whether your minimum temperature is 10 or 20 turns out to make very little difference from the point of view of star formation.
I'll ask you later, but I'm asking about what you would observe in lines from those galaxies and modeling that. So I'll ask you later.
Okay.
Phil.
Yeah, you mentioned the dust cooling might be important in reducing the cooling rate, or in getting enough cooling so that you can form stars. And maybe you can't do it exclusively with just gas line cooling. But wouldn't you also need dust grains to form molecules and put them back into the gas phase in order to get the abundances right?
Yes, yeah.
In these codes?
Yeah. Generally, the dust is done fairly simply. So, I mean, in our models, we just have a fixed kind of dust composition and size distribution that are just calibrated by the local ISM. And then when we look at different metallicities, we just scale that up and down and don't actually change its nature. There are efforts to do that more self-consistently and actually look at how the dust might change as a function of metallicity or environment, but that gets quite complicated. But yes, I mean, you have to include it. The dust is vital for getting the chemical structure right. If you don't have the dust shielding, you're not going to get the right chemical structure in these clouds. And if you don't have the H2 formation on dust grains, you're just going to stay atomic. Yeah, and I mean, I think understanding star formation, I mean, one thing to take away is like above number density 10 to the 5 at solar metallicity, dust is the dominant coolant. So like over most of the orders of magnitude of density, as we go from the low density ISM to forming stars, it's dust. Dust is the thing that's doing your cooling. It's not the molecules. The molecules are really a transient phase. They're interesting because we see them, but they're not, in the end, all that important.
So, one technical question. When you mentioned before, what about Chrome? Would that also be a good option for this?
Yeah, so Chrome is basically it's a package with a whole bunch of different chemical networks. So they have a variety of different reduced networks. I'm not sure if they have a version of the Gong network yet, but I mean those are basically largely taken from the existing literature, and they've just put them all together in a nice simple package. So I mean Chrome is a really useful package if you're interested in putting chemistry into your simulation and you don't already have an implementation, because everything is there in one package. But it's not really an alternative way of doing things. I mean, it's just a nice package for doing the things I've been talking about.
Sometimes if you have to construct a reduced network, you have to do it yourself, because you have to do that for the conditions you're interested in. I know, but you know, I think it's important that you're very careful with the construction of reduced networks.
So yeah, I just want to ask a question for so I understand there is no grain chemistry, but do you have the interaction with grain, so for the freeze out, for instance? Because I think it can change the cooling, for instance, if you are able or not to freeze out CO. But if you have CO remaining in gas, it will keep cooling the gas.
Yeah, so we've looked at this a bit, and I mean the particular issue of freeze out and CO cooling was looked at extensively by Paul Goldsmith about 20 years ago. It turns out that freeze out really doesn't change your thermal balance at all. It's because CO is so optically thick. You can freeze out 99% of it; it's still optically thick, so you still get the same amount of cooling. And so Paul's got a really nice paper showing this, where he just allowed different amounts of the CO to freeze out onto the grains and just solve for the thermal balance of a model core, and it really makes very little difference. And we have done some models of this in simulations, and yeah, we find something pretty similar. And it.
Because you said you can cool the gas up to 10K, and I think when you reach less than 20K, it can change the temperature.
Yeah, but I mean, it's the dust temperature that's important there, not the gas temperature. You're not going to get much freeze out if your gas is 10 Kelvin, if your dust is still 20 Kelvin. On the other hand, once your dust gets down to 10 Kelvin as well, then you do have that being a big effect. Although something that we have found is also important is properly accounting for non-thermal freeze-out. If you just have freeze-out and thermal evaporation, then you find that freeze-out should be really effective and should completely change what you see in CO. And once you then put in non-thermal desorption due to cosmic rays, that completely changes again, and it goes back to being just important at high densities, which I think much better matches what we actually see observationally.
I'm happy you mentioned cosmic rays. So, could you say something about thermal bonds like cosmic rays? Because in the deepest cores, cosmic rays play a very important role, and we know very little about them, even in our galaxy, especially so for other galaxies. I don't know, different conditions. What's the importance of cosmic rays for star formation?
I wish I had a good answer to that question. No, I mean this is something that we're currently looking at, and other people have looked at. So, from the point of view of actually regulating star formation, I would say the cosmic rays are probably not that important, except they may play some role in actually driving galactic scale outflows. From the point of view of what you get in terms of an IMF, that could be a lot more interesting, because cosmic rays give you a way to heat the gas at high densities, even when it's very well shielded from the background radiation. And if you can heat it enough, then yeah, that's potentially going to change the scale on which you're fragmenting and what you get as an IMF. But that's difficult to model. There are claims that cosmic rays could give you a different IMF, but nobody's actually done a fully resolved simulation demonstrating this, because it's hard. So it's something we're working on, but I think we don't yet really know how important that is compared to other effects that we know are important, like feedback from the stars you've already formed. Yeah, and then from the point of view of tracer chemicals, cosmic rays can be important for clearing out a lot of your low-density molecules. So Thomas Bisbas and others have done quite a bit of work showing that if you have a very high cosmic ray flux, you lose a lot of your low-density CO, even in regions that have a lot of dust shielding. And that's potentially going to be an important effect. If you've got a very large number of cosmic rays, it's going to change what your CO and other low-density tracers are actually tracing. Or another way in which cosmic rays might be important, for HCN. HCN is very easily excited with electrons. So if you have enough cosmic rays so that your electron fraction is high, then you actually get much more HCN emission than if you're just relying on molecular collisions. So in normal molecular conditions, that's probably not important, but in somewhere like the CMZ, that might actually be pretty significant.
About the chemical species as tracers, you usually show example of the non-equilibrium post-processing technique from pH simulations. Can you give us more example about application of non-equilibrium on grid codes, or are they really not very much explored because of the difficulty of the tracer?
It's not been much explored yet, mainly because there's not enough people to work on it. And the reason that I've shown you two examples taken from SPH is it's easier to do in SPH because the SPH particles themselves are the tracers, so you don't have to put in additional tracers. But really, there's no huge problem with doing this with any kind of separate Lagrangian tracers. So you could do this in a repo using the tracer particles. You could do this in Flash, or I'm not sure. I think there are tracers in Enzo. But I mean, as long as you have some kind of Lagrangian tracer that you can modify to store the quantities you need to store, then you can do this. It's easier in SPH because there's less bookkeeping.
And otherwise, has anybody tried a hybrid approach? I don't know about the physical states here that you're looking at, but other species or otherwise regimes where you can start to activate a less reduced chemical network at an appropriate amount of time before outputting a snapshot? Like a hybrid.
It's something I've thought a lot about. The difficulty is figuring out when to switch.
Yeah,
So yeah, I mean, I have to move my computer. I think, yeah, there's potentially a really promising technique, but it's not immediately obvious how to do this in a way that ensures you're always self-consistent. I mean, there are some techniques from combustion chemistry that try and do this, but I've never had time to actually work on this for astrochemistry. I mean, there's a lot we can learn from other fields here, because I mean, the folks who do combustion or atmospheric chemistry, they're dealing with advection reaction equations. So they have a lot of techniques that are mostly not used in astrochemistry that we could profitably learn from. I mean, there's some little work being done on this for designing reduced networks. I think Thomas can talk more about that. But there's a surprising amount of stuff that's just never really been tried out for astrochemistry.
It's okay. Thank you, Dan. When we do the intro talks, when the people that are giving them come line up when the speaker is ending, so and everyone's given 2 minutes max.
And now you see the sequence of technologies
Yes.
first.
Hello. Okay. So hi everyone. My name is Feng Long. I'm an SMA fellow here at CFA. So I'd like to show some results from our recent ARMA survey, which looked at young disks in entire southern region. So what makes this survey special is that our sample is selected to be less unbiased in terms of this brightness. So with a typical resolution of 15 AU, we found that many disks show substructures in their millimeter-sized dust grain distribution. So the most common types of structure you can see that is the asymmetric gaps and rings in the systems. And we rarely see spiral patterns or high contrast azimuthal variations. So we found that there's no correlation with this gap or ring location with stellar luminosity which tells us that the ice line hypothesis may not work in all cases. But what if they are caused by planets? Then those young planets should be low-mass neptunes in outer disk. Well, how to form neptunes outside 13 AU in 1 to 2 million year timescale is still a challenge. But in addition to those beautiful rings and gaps, we also found that many disks that are spatially resolved, but without any detection features as shown here. So those smooth disks are distinct from those ring disks in their dust emission radius. So this plot clearly compares the disk radius and brightness for the two samples. You can see clearly that a larger disk will always host dust rings, but a smaller disk are not intrinsically fainter. So the reason behind this size difference is still unclear, but I think it very likely related to the different initial conditions in the disk formation stage. So I hope that this result will be interesting to people who working on disk formation series in this room. We also have a few papers coming out from the survey, so if you're interested in the results, please talk to me afterwards. Thank you.
Good. And interest.
Okay, so I'm Anna. Oh, sorry.
Yeah, no, it's good too.
I'm Anna. You guys hopefully all know me by now. So I'm not going to go into too much detail about the results here, but I just kind of give a brief intro into what I work on. So I use numerical simulations to study how feedback affects massive star formation. I do this by developing new techniques used to model feedback. So I've done a series of papers studying how radiative feedback affects accretion onto massive stars, and also how the initial dynamic state of the cores affect the accretion onto these stars and fragmentation of the cores. And now I'm working on and finishing up some stuff where I also include how outflows and wind feedback, so from massive stars. So once the star gets hot enough, you will expect that these stars will have isotropic fast winds that can actually shock heat the surrounding material, as you see in this picture here. But the main result too is that in all cases, so far as once you have a thick accretion disk around the star, feedback will kind of evacuate material along the poles of the star, but the accretion disk will actually confine the effects of feedback, and you still get accretion onto the star. I'm also looking into how magnetic fields in conjunction with feedback affects accretion onto the stars, and you get very different results when you include magnetic fields. So come talk to me if you have any questions. Thank you.
Yeah. My name is Henrik Beutel. I'm from the Max Planck site in Heidelberg, and I have neither a slide nor a poster, but I hope that you talk to me nevertheless in the end. In general, I would say my interests span a vast range of scales from ISM and star formation physics. Vast range of scales, I would say, from almost Milky Way structures, 200 parsecs or longer, whether they are atomic or molecular, down to the high-mass star formation processes and sub-1,000 AU scales. And we do this in different observational approaches via different large surveys. For example, the Thor survey, that's an H1, and OH, another tracer survey of the Milky Way. And you will see more of this by Yuan and Jonas later. On smaller scales, we are doing this, for example, with the Core survey. That's a large program at the Plateau de Bure, which dissects 20 high-mass star-forming regions. And again, you will also see more by Caroline and Sue about these kind of things. And then we continue and do ALMA projects to do the fragmentation on the smallest scales, but also magnetic field studies. Zooming a little bit out, I would say I'm not so much an equilibrium person, but I think that the whole star formation and ISM formation process are really something extremely dynamical, and we try to trace the gas flows from the largest spatial scales of 100 parsecs down to, in the end, the very inner protostars via the disks. And yeah, it's a very dynamical process. And one thing we could do in a unconference is how to trace these dynamical processes. The tracing is incredibly difficult, and how to do these. That would be one of the things. Thank you very much.
Hello, my name is Will Armentrout. I'm at neither Harvard nor Heidelberg. I'm a postdoc at the Green Bank Observatory. Thank you to everyone for the invitation to be here. Most of my work has been on tracing high-mass star formation regions across the galactic disk. So we're using H2 regions as tracers, and we have a catalog of 8,000 H2 regions and H2 region candidates. One thing you can do if you have a galaxy-wide census is start to trace some galactic structure. Because high-mass stars form preferentially in spiral arms, we're able to try to start to trace some of that structure with these regions. In particular, today I'll be talking about the outer Scutum Centaurus arm, which was discovered by a little telescope that is on top of this building or one of the adjacent buildings, the mini telescope, on top of this building. It is an extension of the Scutum Centaurus arm into the outer first quadrant. So if the sun is right here at this dot, we're looking on the outermost reaches of the first quadrant. It's really the boundary for high-mass star formation within the Milky Way. It's about 22 kiloparsecs from the sun, 15 kiloparsecs from the galactic center. And the reason it wasn't discovered until 2011 is because it warps above the plane of the galaxy. It's so far from the galactic center that it's affected by galactic warp, which we can see through integrated H1 here. It bends up to about 4 degrees above the galactic plane. And so we've discovered 17 new H2 regions in this outer arm and are turning to the Green Bank telescope at 89 gigahertz and 110 gigahertz to trace some of the molecular gas associated with this star formation. So here's one sample region. This was actually discovered through Palomar plates in the Sharpless survey 60 years ago or so. So this region was known, but it wasn't known to be this distant. And again, we have 16 other very distant star formation regions here. I would be happy to talk with you about any of those.
Hello, my name is Sumaya Suri. I'm a postdoc at MPIA. I'm going to shamelessly introduce not one but two of my projects. The first one is, as Henrik introduced briefly, is disk fragmentation and high-mass star formation within the framework of the core project. Does this work? Yeah. So we observed this particular object at very high resolution with the high-frequency band at NOIMA. And this object is particularly interesting because it was discovered 35 years ago by Charlie Latta as an outflow source, but despite the fact that it was speculated that it should be fragmenting, it has never been observed at high resolution until now because it's out of ALMA's reach. So with NOIMA, we detect at least 5 cores at this particular frequency in the continuum emission, and this is also shown in the line emission that we detect, and because we have lines, we can also characterize the disks around the object. My second project is concerning star formation feedback, and this is in collaboration with the Karma and Orion survey team. We discovered this arc, kind of arc-like structure in the southeast of OMC1. And then later we looked at it in multiple wavelengths, and we discovered that this is not a simple arc, but it's composed of many of arcs. And then it also encompasses, this is in O1, it shows the PDR around this region. It also encompasses 2 starless cores and ripples, so instability ripples. And we discovered that this object is not powered, or objects are not powered by one source of feedback, but 3. So they're located in OMC4 and OMC1 South. And this is very interesting. So if you're interested in high mass star formation feedback or disk fragmentation, please come talk to me.
So thanks for all the introductions. I think we now go to the research talk, which is about 12 minutes. So Jen, about course and machine learning.
Cool. All right. So for those of you who didn't know me, might wondering, like, what's this one person from Texas doing here? So the answer is that I was a student with Alyssa. She's still writing letters for me. Thank you. But the longer answer is that, as Alyssa mentioned, Harvard-Heidelberg was the idea of a Harvard-Heidelberg conference actually came about 7 years ago, and that's when I actually started grad school in astronomy. So I think it's fair to say that Harvard-Heidelberg marks the progression of me as an astronomer. And today I'm going to tell you about a story that we've learned with machine learning about the progression of course. And so some review of the history here. There were 3 classes, and then there were 4. So as the progression of, as we've got better and better observations, people start to be able to analyze earlier stages of star formation, and thanks to works done by Phil and others, people start to think about star formation in dense cores and even earlier stages of cores. And the fascinating thing about star formation is that it connects the turbulent molecular components, the clouds, with the stars. So all the way from, like a few hundred particles per cc, or even lower, to stars, the dense stuff, the dense and bright stuff. But even though the most exciting episodes of star formation take place within these gravitationally bound cores, and most studies focus on them, you start to wonder what was before that, right? Like, my career as an astronomer is exciting, but my life before becoming an astronomer also matters. So, Ho Chen, 1991. How do we learn about these cores before they become gravitationally bound? Actually, some observations give us quite important hints on that. So these, here I'm showing maps of 2 different regions. On the left, existing 88 in Ophiuchus. On the right, B5 region in Perseus. And the color codes corresponds to the line width, or the velocity dispersion we measured from with ammonia observations. And as you can see, the brighter regions show where the velocity dispersion is lower or thermally dominated, essentially. So throughout all these different regions, we observe a whole group of what we call coherent regions. So these are essentially regions where we observe velocity dispersion that's thermally dominated. And as you can see, at the periphery of these structures, the change in velocity dispersion is actually quite sharp. But all these coherent structures actually come in different flavors. So for example, on the right-hand side, the first directly observed coherent core hosts star formation at a timescale of a few tens of thousands of years. And on the left-hand side, with the GBT ammonia survey, we see a lot of these coherent structures that are not gravitationally bound, and we have some guess about that. All right, so these are also already very dense structures. All right, so if I take a look at the balance between different energies, for example, on the left-hand side, I'm plotting on the x-axis is the kinetic energy of these structures, and on the y-axis is the gravitational potential energy. As I said, we observed a whole population that's not gravitationally bound. When I compared it to the energy provided by the pressure of the ambient gas turbulent motions, then the turbulent pressure could be enough to keep these structures together. And these structures also have very shallow density profiles. So here I'm comparing the radial density profiles to a critical boundary sphere. These structures have shallower density profiles. On the right-hand side, I also show that the density profiles of these structures are shallower than previous observation of stardust cores. And it seems that these structures are are closely related to turbulence in the dense gas component of our cloud. So, for example, here I'm showing a histogram, a distribution of the
centroid velocity or line of sight velocity of all these structures. And the shape of this distribution resembles what we see as the average line profiles traced by ammonia. So it's intriguing, right? So, but when I tell people about, we found a lot of gravitationally unbound cores, they are coherent, but they're not really bound by cell gravity. Some people told me that it probably has nothing to do with star formation. They are interesting, but like if we want to study star formation, we don't need to care a lot about them. And I say, not really. So if you take a look at biological evolution, the rule of thumb is the survival of the fittest. But we also found many weird, bizarre species that's not the fittest. And why? Because the evolution history is a... Wait. Okay. Because the evolution history is a dynamical one, right? So it just keeps going on. So like at any time step, you don't have to be the fittest, but you can evolve to become, to survive essentially. So after moving to Texas, I started looking into the evolution of the density structures in MHD simulation. And what I do to these simulations that first I extract density structures with dendrogram. You can, it's like you can apply your own favorite, but I love dendrogram. It allows me to extract all the independent density structures in these simulations, and I do two things. On the one hand, I extract because I know where the density structures are. I observe the velocity dispersion profiles, the radial profiles of the velocity dispersion, and the radial profiles of density, and I put them through a principal component analysis, which basically would tell me how different or how similar these different profiles are in a high-dimensional space.
6 more minutes.
6? Okay. So on the other hand, I'm also tracking these structures. So these two are independent from each other. So the result is that, so here I'm showing a distribution of all the structures I extract from simulation in the PCA space. And so, as if two structures are close to each other in this space, then they have similar distributions of velocity dispersion and density. So eventually what I found is that on the left-hand side, I'm color-coding the distribution with the size of coherent regions. On the right-hand side, I'm color-coding the distribution with how steep density profiles are, right? So at the end of the day, I find that there are 3 different groups. So towards the top, there are non-coherent structures with very shallow density profiles. Towards the bottom left, I have coherent structures with mild density profiles. And towards the bottom right, I have essentially self-forming cores. And actually, I can extract that with some simple clustering algorithm. And if I overlay the tracking results on top of it, what I find is that there is actually an evolutionary track connecting these 3 groups. So going from unbound over densities in very turbulent medium, you can, they eventually become coherent structures, and then they would evolve on to become the star-forming cores that we're familiar with. So this is great. So, and if I take a look at the change in the velocity dispersion profiles and the density profiles, so top is the velocity dispersion profiles, you see that the change from the first group to the second group is that coherent regions start to grow in these structures. Turbulence is being dissipated. Meanwhile, the density has not grown a lot during this step. And then only until we go from group 2 to group 3, we start to get the growth in density and gravitational inflow. So really what we're seeing here is a 2-step process that in the first step, 3 steps. So I formed these structures in a turbulent medium as turbulent perturbations maybe. And then the turbulence within these structures starts to get dissipated. And then only after that do we start to get gravitational info. Right. So you can also estimate the timescales, and quite intriguingly, like these timescales agree fairly well with what Mordecai and Ivo Stryker calculated as the turbulent energy dissipation timescales. And lastly, but most importantly, is that if I put these structures in a similar virial analysis, so again, kinetic on the x-axis, gravitational energy along the y-axis, the three groups actually occupy different spaces in this virial space, you can call it. So there seems to exist a evolutionary track that brings all the density structures in the turbulent medium to close to a virial equilibrium, and until only after that these structures start to grow and become gravitationally bound and start forming. So and there is always some variations due to you can start with seeds of different sizes and masses essentially. So right, and that also explains this whole population that we observe with ammonia. They seem to be at different stages, and they could form out of seeds of different sizes and masses. So lastly, I want to show you where these structures are. So in simulation, these structures we find structures both outside and within the densest filaments in the simulation. And so these structures, they essentially form everywhere in this MHD box, and as they evolve, they do not have to be bound. As I said, they evolve dynamically, and they can gravitate towards the denser regions and have the mass reservoir for them to accrete and become star forming. All right. So just to quickly summarize, the observation of bound and unbound coherent structures give us important constraints. All these coherent structures have to form constantly, and they do not have to form gravitationally bound. And there seems to be a prolonged coherent phase in the evolution of cores, and the formation of cores seems to start with the turbulent seeds, followed by a turbulent dissipation, and after that, what we are most familiar with, the gravitational inflow. All right, so I can take questions.
Okay, questions. Let's start with Bill and then.
Very nice work. Can you use these three categories to identify observationally what stage a particular object is in? And when you do that, do you find that young ones are near young ones and old ones are near old ones, or is it all just kind of intermixed and doesn't matter, location doesn't matter?
Yes, we can do that, but yeah, that's of course my plan. So now we have a full evolutionary picture for essentially. We need to identify these structures, their population in clouds. It would be super interesting to look at it, but I haven't for the observations. But I think I can do it with the simulations, and exactly, I think it will be a very interesting thing to look at. Yeah.
How long are the cores expected, or how long are they expected to spend in each of these phases? Oh, there it is.
Yeah.
So that tells you about how many you should expect to observe too, right? As a test.
Yeah. So that's what I would think about Phil's questions. Because now we have a full evolutionary picture, we can do population analysis of observations and to know both the evolution of the cloud and also the formation of cores as they, their relation amongst themselves.
So maybe some of the two Bono objects also carry to
group 3. Yes. So
not to go to 2 and see.
So there is a non-zero chance for group 1 to go directly to group 3, and not all group 1 structures, they are just density structures in a turbulent medium. Some of them are dense enough for them to be close to bound or almost bound already, so they can quickly accrete stuff and become star forming.
Some may not never occur.
Yeah, yeah, and some disperse as well. So there is actually a large proportion, as you can see, right? So we have a lot of different, again, using the analogy to biology, we have different species, and not all of them will survive. But some of them are like evolutionary dead end, but it does not have to be bound to gravitationally bound to survive because it's a dynamical process.
Yeah, so in the simulations, what exactly do you include? So you have like feedback processes also?
So that's one. So this is isothermal MHD with gravity. So the analysis is done on both decaying and driving turbulence, and we only started like initial analysis on simulations with feedback. The takeaway is that there's always these three stages. The physical processes we put in only affect the length of the time scale essentially, but it does not vary by more than an order of magnitude. And the survival rate, as I show here. So with feedback, as you can imagine, some of the structures may get disrupted more easily.
So have you explored at all any of the sort of evolution of the lower level structures of your dendrograms when you're
Yeah, that would be super interesting because everything's ready for that. Exactly. So so I haven't, but I can comment on how easy that would be because as you can imagine, tracking these structures is difficult. That's why there isn't many studies before this. And the most difficult thing would be to those tiny structures, like if you identify, tiny structures at different time steps, how do you correlate them? But if you have like broader, bigger structures, then it's actually easier to track them, and that's definitely our next step.
So, what's the physical mechanism that creates this coherent structure? So is it
right. So
dissipation or what is it?
So again, going back to my algorithm, because dendrogram I only apply dendrogram on the density, so it does not exclude any structure. It basically picks up all the independent density structures. And what I'm guessing is that just with turbulence, sometimes materials can get disturbed enough to have like local density peaks. Because like I have not done a systematic analysis on exactly what creates them, but I would think that they naturally formed in a turbulent environment because
But what are the size scales, say, of these things?
So they're all core. Like these structures start out with like some of them can go up to like point a few parsecs. Some of them are smaller than 0.1 or around 0.1.
It's interesting to compare this, for example, to the sonic scale or things like that.
Yeah, sure.
Scales and see.
Yeah, so other than the size scales, the time scale actually. So I just did this comparison just the other week, and it's actually consistent. This group 1 time scale is actually consistent with the kind of turbulence dissipation that Mordecai and Eve are looking into. And I think in their papers, they're claiming that most of the dissipation occurs because of the existence of a magnetic field, because you get, you can easily channel out the turbulence within these density structures. And I think that's a hint. Yeah.
The opposite question. So what destroys these structures? What process destroys these structures?
Oh, yeah. So, okay. So again, it's very dynamical. All right. So, for example, a lot of the group 1 structures are not gravitationally bound. Okay. So, and as you can imagine, if something that's static, they stay there, and that's not gravitationally bound, they will just get dispersed. But some of them are lucky enough that they may be, the package of material within these structures already have some momentum in it, and they gravitate towards denser region, and they find some mass reservoir, and they are lucky enough to evolve on. So, so these structures get dispersed naturally in a turbulent medium as they are turbulent structures. And but some initial look with the simulation with feedback is that feedback destroys them. Right. So like I think So that's my best answer right now. I agree. Like more systematic analysis needs to be done.
We have to stop here.
Yeah.
The topic for a conference session on.
Thank you, Tom.
Okay. Thank you.
Thank you.
Move now.
Yeah, so just so if you don't, raise your hand if you know where Fort Simon House is. Okay, so follow one of these people across the street. Right? So Mike will let you then go to the door. Mike has red hair, it's very easy to see him.